their way into the iOS 6 release. And I know this because the creator of them sits somewhere here in the audience. Keep in mind, they only work with Objective-C. Our class is exported to Objective-C. However, since you're using UIKit, this shouldn't really be a problem because it is Objective-C. Now, the names should be kind of self-explanatory. Iva description, I would say, is the most useful one. It's kind of funny that Apple uses this method to debug issues in third-party code, and we use it to debug issues in UIKit. So there's a few more useful hidden methods specifically for debugging. And also don't forget, Xcode has this amazingly great visual debugging tool. And if you need even more, there's Reveal from itty bitty apps. So you can even debug your view hierarchy while the app is running. But my focus here is on LLDB. And many times you just want to verify if an object you're currently looking at indeed is in the hierarchy, has specific subviews, and so on. And so using the console is by far the fastest. There is recursive description on UI view. There is print hierarchy on UI view controller. And of course, there is auto layout trace. And I'd like to give a specific shout out to the UI view layout feedback loop debugger, which Apple added in iOS 10. However, when you Google it, you'll find a few Chinese websites and like almost nothing. It was a little bit under the radar, not because Apple tried to hide it. There's a 12-minute session on one WWDC video. It's just that nobody saw it, or like not many people know that it exists. If you have an issue where suddenly you click somewhere and things start to crash, and they start to crash by piling up memory, this probably is a layout view issue loop. That's an amazing tool to debug. And these methods are all a little bit trickier to call from Swift. So here is the reminder for the correct syntax. And some people prefer to declare these private methods as categories, so they're easy to call in Swift. But really, there is no need to pollute your project with additional code. We are the lazy smart engineers here, and we want to make shortcuts, right? So you can create a shortcut in LLDB init. If that file isn't in your home directory yet, just create it and then add that line. And now, thinking about it, of course, there are already open source projects that do just that and much, much more. So Facebook has a collection of one-liners and script for just about everything I just talked about and more. There is pviews for, you guessed it, printing views. PVC does the same for controllers. There are helpers for accessibility, for marking views, for putting borders around it, for showing properties of objects. Slow anim can slow down animations. It's kind of like the menu option in the simulator, just that it also works on the device. There are helpers to visualize data as an image. You can use regular expression, you toggle layer visibility, you can apply masks, set breakpoints on instance variables, print actions, print the responder chain, and much more. Whew. But since January of this year, there's one command to rule them all. And that's called findinstances. So this scans the memory, the whole heap, and uses heuristics to identify instances of Objective-C classes. This, of course, also includes Swift classes that are descend from NSObject. You can literally do queries such as, show me all views that do not have subviews. Give me all instances of array with more than 100 items. Show me all my instances that implement UI scroll view delegate. Show me all views that are currently hidden or have no window, are transparent, or have a size of 0. You can even dig into dictionaries, and you can do even more complex commands. This works by scanning the heap, so it actually injects code in your app. So the one downside is that currently it only works in the simulator. I'm sure it could also be made to work on the device, just nobody did that so far. Now, I did tweet about Chisel a few times, but haven't really seen many people using it. This is really a killer feature for better view debugging. Now, Chisel is convenient to find instances. However, there is yet another way to find your objects. Xcode 8 gave us an extremely convenient memory graph debugger. Before the memory graph debugger gets useful, enable malloc stack logging. You can switch here between live allocations and all allocations. The former is enough to find retain cycles, and the other one is a little bit slower, but covers all objects. And it hides under that button. So this is how it looks. This view basically answers the question, why does an object exist in memory? And in some ways, it duplicates functionality from instruments, but it directly integrates into Xcode. And you can use it at any time during debugging. On the left side, you see all classes in memory. On the right side, it shows the backtrace when the object was created. And the main area shows you the object reference graph. Now, where is this useful? We had an issue where scrolling very fast through a document caused temporary memory spikes. So let's see if this works. Yeah. So I made a video to show you a little bit what's going on. You see that scrolling normally is fine, but if you start scrolling and zooming like a madman, I'm doing that right now. No? Yeah. There are huge memory spikes. So this doesn't happen in the simulator. So of course, I cannot use find instances. And my hypothesis was that something is retaining the images that we render here too long. So for the second spike, I pressed the memory graph debugger button just in the right moment. It takes a while to load. And then I searched for your image to find all the images in the debugger. However, as you see, there are like 155 instances. And a lot of them are bar button items or normal UI stuff. And I can't really do predicates here. I can't filter for size. So what do we do? In this case, I used a clever hack, and I marked the images as subclasses. So this might not work for all the cases, because your image is actually a class cluster. It can be asset images, animated images, and I don't even know what else. But it does work for the general case. And just before we return the image, we just call Objc set class and replace the image class with our empty image class subclass. And after doing that, I can do the whole process again. And instead of filtering for your image, I filter for, in my case, PSPF rendered image. And then I see just the instances that I'm interested in. And you see there are still too many around, 99 in that case. And when you select a few, you see exactly who retains these images. And in this case, I kind of reconstructed the bug, because the original bug was quite a bit more complex. But you see that I made a block that just calls 2 seconds later and basically holds the image for 2 seconds. So when you scroll fast, that's how you get this spike. And you see on the graph that it's very easy to identify what's wrong. Now, this bug took quite a while to verify, and because it wasn't as drastic as it showed in the simulator. There were the crash reports that you usually get are not very conclusive. So you can try for yourself if it's fixed or not. And that's a shameless promo. I copied the QR code idea from Mike. Now let's talk a little bit about the Clang Analyzer. This is a really, really powerful tool. And when I say powerful, I say, holy, yeah. So this was actually a real bug in a low-level dependency in our framework. And you could probably stare for hours at this code, and you wouldn't find this particular, it's an out-of-bound memory access, you know, the real nasty kind of thing. And the way we used it would have probably never happened, but it still was a valid bug, and Analyzer found it. So always run Analyzer and make sure that you don't have any warnings. Now, you all know that Analyzer exists, right? But what's less well known is that there are optional checkers that are not enabled by default. So if you just type in this command, clang cc1 analyzer checker help, it will give you a long list of all the checkers, of all the ones that are enabled, and all the ones that are opt-in, and the ones that are still in alpha stage. So one that's very useful that's still alpha is a check for bool. You know, Apple fixed bool on the ARM64 runtime, but for all the other runtimes, it's actually a character. So you could set it to 42, and that's not very useful, so there is no analyzer checker that tries to find such problems. Another one that's very promising is the clone checker, which reports similar pieces of code. However, that one is not quite ready yet. You will get a lot of output. Some are also, or maybe our code is just bad. Some are also very C++ specific or more specific to system programming, but I'm sure you'll find a few checkers that are useful to you that you haven't seen yet. So the list that we use is quite large. The syntax, how to enable it, is a little bit unusual, so you can just copy that later from my slides. I'll share them on Twitter. And whenever you face a false positive, it's easy to just disable Clang for a particular line of code. But before you do that, check if there is not an attribute that can tell Clang what happens. So for example, there is an opt-in checker for non-localized strings. However, in any large code base, there will be some strings that are not meant to be localized. And Clang doesn't know that and will happily warn about any string that it finds. And instead of disabling the Clang analyzer for all those things, you can pass your string to a method that you annotate with returns localized string. So you mark the string as, this is OK, I don't need to localize it, and Clang will be happy. Now, let's talk only shortly about warnings. I'll keep it short because this only applies to C-based languages. Swift is taking a different stance and doesn't allow you to modify the warning set. The intent here is that the Swift creators don't want the language to create dialects, and this is very much the case in C-based languages. But if you have C, C++, Objective-C in your project, I recommend using W everything. That's kind of what some people call Xcode hard mode. Just disable all the warnings that do not make sense for your project. Now, this can be quite a lot of warnings. So this is actually our warning configuration that we ship. There's a lot of warnings, but a lot of them that don't really make sense or are more like of an informative nature. So don't be afraid to disable a few warnings. And also notice a handy trick when you configure your project via xcconfig files and you want to use more than one Xcode version, especially warnings get added all the time, even in minor releases of Xcode. So you can use Xcode version minor as a replacement tag. So you have your base set, and then you can have your extension set, and depending on what version of Xcode you use, it will automatically pick the right thing, and you don't have to do any configuration changes if you want to switch from stable to a beta version. And of course, with Pragma Clang diagnostic, you can always opt out for a warning for a specific region of code. All right, sanitizers. So the various sanitizers that Clang offers are all great in helping you to find or even better prevent bugs. The address sanitizer is a fast memory error detector. It's based both on compiler instrumentation and the runtime library. So what it does is it has a shadow memory region. So whenever you access something in the memory, it checks if you're actually allowed to access it. And if not, it will promptly assert and crash. The slowdown is a very acceptable 2x. We have this always enabled for our tests. It rarely finds issues, but the issues that the address sanitizer finds are usually very nasty, usually out of bounds memory accesses, heap corruption, the kind where you will have a very hard time to debug and find things. So keep ASON on for your tests. The undefined behavior sanitizer will find things such as nullability violations, integer overflows, divisions by 0, and other nasty things in C-based languages. There is no Swift support because Swift does most of that in the language directly. The overhead is around 20%, so it's barely noticeable. And in fact, the latest Clang 6 even added a mode that allows you to ship UBSUN at runtime. So it's not sure if Apple will actually add support for that in iOS, but this is something that can make C-based languages quite a little bit safer. The main threads checker isn't strictly speaking, a sanitizer, but something you should always keep on. You can only access UIKit from the main thread, and if you violate it, you can have bugs like, why does my label update 5 seconds later? And those are also very annoying. The main thread checker is really, really good at finding those things. The last one in our list is the thread sanitizer. And this one has a considerable slowdown. So things will run 10 to 15 times slower. It's 10 times as much memory. And you cannot even run it at the same time with the address sanitizer. However, it finds races that will blow your mind. It definitely made me a more conscious programmer by seeing where the thread sanitizer triggers. So what we do is we have this on CI because our test case takes around 40 minutes. If the thread sanitizer is enabled, it's multiple hours. So you want to have a dedicated computer that gives you the output. It even has a basic form of deadlock detection. So Xcode makes it really simple to enable all these sanitizers. And also good to know, every sanitizer has advanced options that are not part of the Xcode UI. So I do recommend actually just reading the Chromium open source repository or the Google Wiki, because this is kind of like the best resource that's on there next to reading the actual source code. This is all woefully underdocumented. But we, for example, we needed to add a suppression list because there was some Apple code that triggered in the address sanitizer, and there's really nothing we can do other than file a radar. So we excluded it. And yeah, I recommend that you share this in your project, especially if you have multiple targets. All right, the fun part. So even if you enable all the warnings, all the analyzer checkers, and all the sanitizers, you will still have bugs. And this one here is a particular fun one. So everyone knows the message sent to deallocated instance warning. When you debug a crash, enable zombies. Things get really interesting when such a crash happens on a global background queue in an auto-release pool pop. So this bug randomly appeared while I was working on fixing another bug. And I was immediately hooked. This shouldn't happen. This shouldn't happen at all. Now people who worked on the Mac platform long enough to remember manual retain release, they will know these kind of issues. But Arc does a really, really good job at making sure over releases are no longer an issue. Still, here I was with this impossible crash at midnight, desperate to find a solution. So the first thing that baffled me was it's an unnamed background queue. And what we do is we name all our background queues. And I actually consider it a bad practice to just throw a task in a background queue without giving it a name. Just wrap it into your own serial queue. GCD queues are really, really cheap. And when you pause, it's much, much nicer to see what's going on. And yeah, I'm sorry for all the Objective-C here. Our framework is a lot of Objective-C and C++. We cannot use Swift yet because it's not yet binary compatible. Of course, I switched on all the sanitizers, but other than lengthy recompiles, they didn't help. The root cause here is that somebody calls auto-release on the document in a background queue. So let's set a breakpoint, right? The problem is with Arc, this doesn't work anymore because Arc doesn't use message passing for retain counting because calling that directly is faster. So the compiler instead emits Objective-C retain or Swift retain or whatever's appropriate for that object. And setting a breakpoint on Objective-C auto-release, even if that would work, would be impossible because it's just used everywhere in your application. Even if you somehow manage to make it conditional, it would be too slow. However, we also know that Arc works with classes that implement their own custom retain release counting. Because there is legacy, there's a lot of legacy, especially in AppKit. So there is a runtime check to check if a document implements those methods, and then Arc goes down a slow path. And this is what we want to abuse here. So I just went in and, okay, let's implement auto-release. But again, of course, Arc forbids you to do that, because that would be slow, and that's usually not what you want. And converting my whole class to manual memory management, probably not going to happen. I would probably make at least 10 new bugs, so this is definitely not something that would work either. But we can just use a different class. So because it's not the first time I had this problem, we already have a class that's called retain tracker, which is basically just a subclass of NSObject that implements retain, release, and auto. Prints the stack trace, so it's very much Stone Age debugging. And we do one nice tweak, and we just don't print the main thread calls, because we know that the bug happens on the background queue. So we can already filter out a lot of things. Now, the problem was that document is kind of our core class. The whole thing was in the viewer app, so there were multiple frameworks. The debug helper was very much low level, and I couldn't just reference it because I would get a module references blah, blah, blah error. So what to do? Objective-C runtime to the rescue. Instead of modifying all my headers to drag that one up, I just use class set superclass at runtime, and I replace the superclass of PSPDF document, which is NSObject, with the PSPDF retain tracker. And because I'm really lazy, I didn't even import a file. I just use NSClass from string. Good enough, works. And now, if you've never heard about class set superclass, there's a really good reason for it. Do not use it in production. Of course, I did use it in production, and things went horribly wrong. But if you want that story, ask me later on after I had a drink. And just check out the header file. Apple is pretty blunt about it and says, you shouldn't use this function and not recommended. But you know, like, we are debugging here, so we need the heavy weapons, right? And sure enough, this actually worked. So running the tests gets really, really slow. It spits out a ton of log messages and stack traces, but eventually it crashed. And you know, like, we are in debug mode here, so Arc is really dumb and does call a lot of retain and release. It only gets smart and optimizes when you're actually optimizing your call. So copy everything, copy it into a text editor that actually works, and then try searching. And we are searching for auto-release and then the background queue. So I'll zoom a little bit in here and show you the important parts. So during deallocation, one of our render tasks, the document was retained at the render task, and then the document was deallocated. Inside the dialog of the document, we did some cleanup, and one of the things was that we send a notification that the document is going away. And there is another class, our cache hash manager, a stupid name. It listens to the close event, and it does run following code. So there is a will close document, it does some simple checks and does some housekeeping. And this used to work because in earlier versions, we just did a manual cast here. Because notification object can only ever be the document. However, years of writing code made me a grumpy, old, suspicious developer. So as part of fixing the other bug, I added a check and changed the ccast to a checked cast. So this is C++, but it's very easy to understand. It basically uses an is kind of class. It checks if object really is the document, and if not, we crash. So the helper here is really quite optimized and cheap. But in debug, Arc emitted an auto-release call for the helper. And you know that calling auto-release inside dialog is really, really not a good idea. And you can use the assembly view in Xcode to actually verify what's being created and where this auto-release is coming from. And you see that our beautiful call is now called something like set n5 ps blah, blah, blah. It's mangled because you have to mangle complex classes, similar to Swift. And right below, you see that there's the retain auto-release return value. And that's exactly what we don't want. So look at the helper. It's simple code. I mean, ignore the template stuff, but it's simple. And it already has inline in there, so it should be inline, right? The problem is that compilers are old, and people abused inline. So inline now is more of a recommendation for the compiler. It just says, hey, maybe you should inline it. If you want to inline something, you actually need to call attribute always inline. And that's it. That's the fix. One word. To recap, best debugging is no debugging. Brew install Chisel so you get your find instances. Use the warnings and enable Xcode hard mode. Use the sanitizers. Remember the memory graph debugger. And when you're debugging, anything goes. Thanks for listening.